Hello, everyone, and welcome to our second webinar for today. I am Mohammed Al Zajjali, petroleum engineering student at University of Oklahoma, and I will be your moderator for this amazing webinar. Our webinar today is about Introduction to Gas Lift, which will be presented by Dr. Ahmed Mahmoud. Dr. Ahmed is assistant professor at AUC. Dr. Ahmed holds a PhD degree in petroleum engineering from Imperial College London and master degree from Heriot-Watt University in reservoir engineering and a bachelor degree from Cairo University. Dr. Ahmed was a researcher at the Royal School of Mines in Imperial College London and is currently assistant professor of petroleum engineering at the Petroleum Engineering Department at the American University in Cairo, AUC. He has more than 20 years of diverse international experience and held a variety of technical positions in production and petroleum engineering, and is recognized as an expert in tight gas sandstone reservoir in both reservoir modeling and production enhancement artificial lift. He has led several mega-sized gas fields projects at an international level in Europe, Africa, and Middle East. He has 18 international publications, several industry-funded research grants, and has been on enormous SPE committees. It's our pleasure to have you today, Dr. Ahmed, and the mic is definitely yours.
Thank you, Muhammad, for this introduction. And I welcome everybody who is joining us, as well as everybody who will be watching us later on the YouTube channel to this webinar about Introduction to Gas Lift. In this webinar, we will go over the main, most important items that are related to all the aspects of gas lift engineering. We'll cover it. And after that, I will give you a couple of references if you want to go any deeper in things related to gas lift. Okay, so this will be the agenda which we will go through today. Primarily, we will review the basic production evaluation and the basic production system in the oil and gas and petroleum industry. And from there on, we will take the next step into the production enhancement criteria. That is, if the production system is not producing at the rates we want, at the production we want, then what options or criteria do we have to increase and improve this production? From there on, we will lead ourselves into the things which we can have that will lead us to take the decision to decide of gas lift as our artificial lift system or as the production enhancement solution which we will decide on. And then we will go over the basic gas lift concept, and we will go a little bit in depth with that in terms of the different gas lift methods. And we will wrap it up with gas lift applications and how the gas lift industry has now reached the level as it is now in the 20th century. As you all know, gas lift actually started so many years ago, back in the black and white days, and it's still being used a lot. A lot of operating companies use it. It's very cost efficient if you have big fields that do have good production potential. Okay, so first of all, I would like to review the basic production system and how we evaluate it. And it's very important for me for everybody to be in line with us, whether you've seen this before, whether you know it or not. It's very important to have the basics or the foundations of the basic production system well established before we take steps into whichever direction of artificial lift system or gas lift system in particular. So this is the typical or the simplified form of the basic production system. And we start with the reservoir, and from the reservoir, the oil migrates to the wellbore. And there's a motivation for this migration. And the motivation for this migration is the change of pressure. The pressure in the reservoir is high. The pressure in the wellbore, which is a man-made thing, is definitely going to be lower. So there's a motivation for the oil or the hydrocarbon in the reservoir to make this immigration process and go into a lower pressure into the wellbore. And here we introduce PWF, which is the pressure in the wellbore. Okay, yeah, flowing wellbore pressure. And from there on, after we have passed these 2 points and passed the main bridge between the reservoir and the wellbore, meaning the perforation or the casing, the oil needs to travel all the way up to the wellhead. And in this migration process, we are actually initiating or we are asking oil to flow in the opposite direction of gravity. This is something which we want it to move from south to north, where typically Newton's law of gravity, everything will fall by gravity, so it will move from north to south. And to do this, to motivate this migration process from the wellbore to the wellhead, we will pass by the tubing. And the tubing needs to have a delta P here, which will motivate the motion, the traveling, the distance of travel needs to be motivated by the delta P pressure from the wellbore to the wellhead. And en route of this process, we will typically be passing by the tubing. And this distance is pretty big, and it represents the main traveling distance, which is against the rule of gravity. Once we are at the wellhead, we have a horizontal migration process, and it will travel to the separator. This is easy because en route to the separator, we have the choke where we can actually be manipulating the delta P and changing the pressures to enable the wellhead pressure to remain higher than the separator pressure. And then the very final stage of the migration process from the separator to the stock tank. And this is the easiest thing. Obviously, the separator pressure will be higher than the stock tank or the storage tank pressure. Okay, so what do we need to take into account here? The main thing I want to leave with you from the slide is this, is that the flow of the entire immigration process, starting from the reservoir into the wellbore, through the tubing up north, from the wellbore to the separator, from the separator to the stock tank, the flow is initiated due to delta P, which is okay. It's good and easy. In wells that have enough reservoir pressure, enough potential, they will have enough delta P's to spend and keep on losing throughout this process to be able to reach the stock tank. And that's okay. But a very big part of this delta P that is initiated or that is compensated in the tubing is lost in the tubing. And some wells, reservoirs in particular, may not be that strong. They may not have enough reservoir pressure that will be able to pay this delta P tax, if we can say, to be able to travel this distance up north from the wellbore to the wellhead. And because they don't have enough delta P, I need to reduce the pressure by lightening the fluid column, because the weight of the oil column is heavy, and it is heavy enough, and the reservoir pressure and the wellbore pressure do not have enough pushing force to push it up north. So I need to add a method to lighten this fluid column, to lift this burden, this hydrostatic burden, off the shoulders of the wellbore and the reservoir pressure, so that when this burden is light, it will be able to push the fluid up to the wellhead, through the flow line, to the separator, and all the way up to the tank. And the way we do this is basically we start injecting gas in the annulus, and we don't inject it randomly. This gas injected in the annulus goes into a couple of gas lift valves that are well regulated. The mixture of the oil and the gas lighten the density of the gas, reduces the hydrostatic pressure, lightens the total burden of fluid weight on in the tubing and acting on the wellbore, and it will have enough force to push and apply delta P, which will be able to now deliver hydrocarbon fluids to the wellhead and complete the complete cycle all the way up to the stock tank. Okay, so how do I monitor that and how do I evaluate that and what is the basic data of our evaluation process, whether it is a gas lift or any other system, as we said and we discussed in the previous webinar. We use something called the IPR curve. And the IPR curve stands for the inflow performance measure. And it's a method which is used by petroleum engineers. It's very similar to what doctors use in the medical domain. It's basically a diagnostic tool or a health check, if we can call it. And we use this IPR curve as a measuring tool to identify and decide if this well is producing at its optimum production, not producing at its optimum production. If it's not producing, what can we do? And then we open our option lists and we start discussing them one by one until we shortlist them and then decide on the best artificial lift system we want to go to. Okay, so this is what the IPR curve looks like. And we'll take it step by step in the next couple of slides just to make sure that everybody with us is in line and at the same level before we start to take deeper steps into gas lift. We will have the inflow curve and the outflow curve, and we plot them both together on the same plot. And when you plot them both together on the same plot, it's called inflow performance relation. And the inflow curve, which is in red here, okay, this is in the case if you have gas component within your hydrocarbon, and it will be a straight line if you don't have a gas component, if you just have liquid. And the outflow curve will always take this shape, which is similar to the tick shape, and we discussed this in detail in our previous webinar. So the inflow is affected by a couple of factors that affect its performance, and it will affect whether it's inclined, half inclined, and how the inclination takes place. But there's one thing that doesn't change in the inflow, which is the initial reservoir. Unless you are going to change that, it's another story, we'll talk about it separately. But the starting point of the inflow has to be the initial reservoir pressure. From there on, it moves down, and it moves down affected by these couple of things, mainly productivity, permeability, reservoir pressure, and skin damage. On the other side, the outflow curve is affected by a couple of other things. The outflow curve is basically anything starting from inside the wellbore all the way up north. Okay? So you'll have the tubing size, the water cut, the GOR, and the injected gas lift, which we'll talk about today in detail. Size of the subsurface safety valve, the choke size, the wellhead back pressure. So everything from the wellbore up north affects outflow. Everything from the reservoir to the wellbore is inflow. Okay? Now, if we consider that this is the well and we are going to start with this node right over here, which I have the pointer on, and then we install the tubing, and then after that, flow comes in, and the flow, anything coming from the wellbore up north is everything that affects outflow. And when I plot this on this chart or this plot with pressure in the y-axis and Q in the x-axis, and I plot my outflow curve, then I'll be able to determine my Q at any given time and at any given pressure throughout this entire well completion system. And in the inflow, it's exactly the opposite. The inflow, as I mentioned before, starts from the reservoir pressure, and it will go down all the way up to, let's say, where the stock tank is. So this will be, let's say, atmospheric pressure at 14.7. Okay, so this is inflow and this is outflow. And when we put both together, we will get the inflow and outflow on the IPR curve. Where they intersect, we will call this the solution point. And if you have a solution point, that means you're in business. Okay? Because the solution point is the point which will decide that you have Q and you have a naturally flowing well. So you're in good shape. Because from here on, we can start to take even better steps if we want to enhance the queue. What can we do? Do we change things related to inflow or do we change things related to outflow? Okay, obviously we will be aiming to move the queue to the right in order to increase the queue. And there are multiple ways, multiple methods we can do to increase the queue. Okay, that was in the good cases where you have an actual flowing wave. Now, if you have your outflow curve not intersecting with your inflow curve, then you do not have a point of intersection. You do not have a solution point, and that means we have a problem. And this is your role as a production engineer or a student about to graduate. Your role is to find methods to compensate for this delta P to get these two curves, inflow and outflow, to intersect. And it's up to you. There are ways you can do where you start moving outflow or you can start moving inflow, but we need them to intersect to be able to get a well flow. And in this case, okay, or in this webinar in particular, because there is no flow, we can have a gas lift completion system installed. So you have gas lift and the gas will start entering. When the gas starts entering, it actually reduces the delta P. And in this reduction of this delta P, basically I'm reducing this change of this difference in delta P, which I don't have, in order to get both the inflow and the outflow to cross at a solution point. And once it's crossed at the solution point, then I will get a Q, and this will closely resemble the natural flow criteria by reducing the hydrostatic column in the Q. Okay, so we've been through the production part. Now let's go into the production enhancement selection criteria. What criteria do I have to choose if my outflow and my inflow do not intersect? And primarily, we can take this option. So this is my inflow, and my inflow, as I said before, has to start at my initial reservoir pressure. But I can change that. I can be adding things, okay, which are pretty expensive in these cases. Water injection, gas injection, their setup is very expensive, meaning surface facilities. Or you can be doing WAG, water alternating gas, in which case you will be actually shifting the reservoir pressure up. And fine, if this is the case where you do have economic justification, you can shift the inflow curve up so that it intersects with your outflow. Once you have the intersection, you have a solution point, you have Q, you're in business. And there's another option we can do, is that we can actually be moving the inflow in terms of an inclination, okay? And in this case, my reservoir pressure will stay the same. I will just be doing reperforation, acidizing, or fracturing as an induced hydraulic fracture in order to change the inclination of the inflow and have an intersection with my outflow. Here I have an intersection point. That means I have a solution point, and I will have Q, and then I'm back in business. Okay, and there are other things we can do. So anything related, I mean, the previous couple of slides, what we discussed are things related to changing the inflow. And methods and solutions that are used to change the inflow are typically very expensive, whether it is gas injection, water injection, or even fracturing and matrix acidizing, relatively expensive. But there's another thing we can do, is basically, if we leave the inflow line as is, we don't play with it because it's very expensive to move it up and down. And we can be doing cheaper methods, more economical methods, to move the outflow curve down to have an intersection. And one of the methods which we can do to move the outflow curve down is by using artificial lift methods. And there are multiple methods, but the method we're talking about today specifically is related to gas. Now, typically, if the well is not flowing, the liquid gradient will have an inclination or a gradient where it is below the wellhead pressure depth. So the typical gradient of the fluid level is below in terms of depth. The well has a static liquid level lower than ground level or the wellhead pressure or the wellhead by itself. Now, to change that in gas lift, I want to change this gradient line so that I can deliver fluid to the wellhead with pressure. And to do that, we do gas injection, and this gas injection will change the gradient line inclination and be able to deliver hydrocarbons to surface at a positive pressure. Okay, so that was the concept. Let's go a little bit deeper into how can we select and confirm so that we are confident that gas lift is the solution for us. Now, first of all, let's define the definition of gas lift as I mentioned to you all before. So gas lift is defined as a method used to lighten the fluid column in the well tubing by injection of gas at different tubing depth, thus reducing the hydrostatic. This is the main aim. This is the meat I want to pass to you all today. Okay, reducing the hydrostatic and enabling flow in a way which is mimicking or similar to natural flow. Okay, now to select an artificial lift method, I will have multiple solutions. I can be doing sucker rod, hydraulic jet pump, gravity pump, ESPs, and there are other webinars that spoke about it in detail. Now, for me to identify that gas lift is my solution, this is my best solution, first of all, I need to know that the efficiency of gas lift is between 20 to 30%. Okay? But still, even though this 20 to 30% might look low as compared to other methods, it still might be a good solution for me, the optimum solution for me. So how do I confirm that? So the first thing I need to do is that I need to identify that my maximum well depth is not more than 15,000 feet. The next thing is that I need to be sure that I'm in a high volume area. That means I'm dealing with a field that can produce a lot of barrels of oil, meaning that it is at the limit which the gas lift can deliver up to 30,000 barrels of oil per day. If I have these two criteria, then I'll be able to justify it, and I'll show you now in the next couple of slides why we need to have high volume and why do we consider that gas lift is a high volume method. Because there's quite a lot of capex and investments that needs to be done. But gas lift, if you are in wells up to 15,000 feet and you can produce up to 30,000 barrels of oil per day, gas lift is an option. Now, how do I go into the selection criteria to make sure that I am in the correct method that is required? I will do the initial technical screening by making sure that gas lift can deliver to me the amount of delta P required to have my inflow and my outflow curves intersect. That's number one. Number two, the name of the game is gas lift. I need to have gas, and I need to have a lot of gas. Okay? I need to have gas to be able to have surplus gas, which I can use to get my gas lift system to work for hundreds of wells. So I need to have gas availability. The field needs to be large enough. Okay, this is not an application for a single well solution. Okay, in other methods, you can have whatever artificial lift you can select that will be applicable for 1, 2, or up to 10 wells. But gas lift is a method you need to apply throughout an entire field. You need to have a large field. You need to have a lot of gas, and you need to have large volumes as well. Now, the other thing related to the actual property of the reservoirs and hydrocarbon is that you need to be producing a little bit of low viscosity. Because if you have a high viscosity crude, okay, gas lift may not be the solution for you because you're going to have to be spending quite a lot of gas to lighten the fluid, okay? But if you have low viscosity, then it's okay. Gas lift will fit and it will fit well. Obviously, GUR, the main advantage of gas lift, why a lot of people use it, is sand and the depth. Even if you have sand being produced with the oil, gas lifts will still be able to lift it to surface. Even if you have deep wells, gas lift valves can go deeper up to the 15,000 foot mark as we discussed before. It's applicable onshore and offshore, and the efficiency of 20 to 30% is not that bad. It's still good considering that you're using it on a large field scale. And obviously, the lifting cost compared to the volume is very good, and I'll show you now, okay? Particularly when we go into the momentum. Now, this is what we discussed previously, if you watched the previous webinar, but all artificial lift systems, okay, fall within the momentum concept. Okay, they all fall as per the law of Archimedes, okay, that said, give me a big enough lever and I can move it. And the good thing about this is that this is the concept which is used by humans ever since the start of civilization. And this is how people developed in industries, developed in civilizations, developed. And it's the concept of magnification. Okay? And the concept of magnification or the momentum basically enables a small kid on one side of the lever to be able to lift a full adult, okay, by applying a small force. He can be actually magnifying the amount of power he is putting in order to get something more. And this concept of momentum is also applicable for all artificial lift systems and for gas lift. So what's the momentum part in gas lift? Okay, the momentum part in gas lift is basically based on my ability to combine these three things together, and the surface facilities, the well completion, and the gas lift mechanism, and I'll be able to have this full momentum lever system that will be able, I can apply a small amount of gas and get a very big volume of oil coming out. Okay, so let's go into the basic gas lift concept within these three main criteria, one by one, step by step. First of all, let's see the surface facilities. Okay, I guess this explains why initially we said that gas lift is a system that has to be applied on large fields. Okay, because the surface facilities is big, it's huge, and it's expensive. Okay, the compressor stations by themselves, you need very big compressors that cost quite a fortune to put them together. Okay, and you're going to be compressing gas, and in this actual process, you are actually also recycling gas. And after the compressor starts working, you will be injecting some gas into the pipeline system, which will deliver this gas to the well anyways. Now, what gas am I going to be injecting here? First of all, you know that this is the export gas, and the export gas will typically be the good gas, the expensive gas, the gas everybody wants to buy, the gas that can be liquefied. Okay, and the gas which is not sellable is the gas with heavy components, the low quality gas. This gas I can use to recycle it throughout my field, inject it within the annulus, okay, and I use it within the gas lift mechanism or system to lift oil, and the situation or the cycle keeps on going on and on. So where's the momentum effect here? The momentum effect is based on gas, because gas is a compressible fluid, and I can compress gas, and the gas can expand, and this expansion and contraction of gas will provide the momentum effect that will be able to lift fluid to surface. And The momentum effect is there by itself in terms of cost. You're injecting gas, and not just any gas, low quality gas, which is typically the cheapest gas. Okay, and you are in return getting oil, which is typically being sold at least 10 times, okay, the price of the gas you had injected. Okay, so what's the completion part? Okay, now the completion part is basically I will have a well, and within the well completion, I will have gas lift valves pre-installed within the completion. Okay, and I will inject gas, as I mentioned before, and this gas will come in and start opening the valves, and I will show you later in detail how the valves are opened. And in return, I have reduced the hydrostatic column in the well tubing, and as a result, I will get production of fluids coming out here. And if I put this on the gradient curve, this is my optimum solution. The reservoir pressure can hardly deliver with a pressure to the depth of the lowest most gas valve. From there on, I will take it on my shoulder to reduce the delta P, okay, by injecting gas and being able to deliver the hydrocarbons liquid all the way up to surface. Okay, so let's summarize the mechanism in a nutshell, the gas lift mechanism in a nutshell. First of all, gas is injected in the annulus, okay? And once the gas is injected in the annulus, these valves do not open all together. They open one by one, and I will show you this later in detail. But once I inject gas in the annulus, the gas will start to open the valves, and the valves will open, and the gas will now be injected inside the tubing. Once it's injected inside the tubing, it will commingle with the fluids inside the tubing, reduce the hydrostatic, and then it will lighten the total fluid column here. Once that is done, the next thing that will automatically be occurring, okay, is basically I have reduced the overburden pressure on top of the pressure in the wellbore by lightening this fluid column, and then I'm actually attracting, helping more oil to flow from the reservoir into the wellbore and the process goes on. Okay, now there are two sorts of gas lift systems that can be applied, and it's very important for me to make sure that within this webinar the issue is very clear, because I realize that a lot of students are actually confused between continuous gas lift and intermittent gas lift, and I want to make sure that it is clear. Okay, and we'll take it step by step by comparing both methods. When do you use each one and what is the application? So for the case of continuous gas lift, okay, the concept is based on three things: reduction, expansion, and displacement. First of all, it's the reduction of the fluid density and weight column. Initially, I inject gas, and this gas is dissolved inside the fluid, and then this gas starts to expand, and the gas bubbles start to commingle together, and they become bigger bubbles, and then they become even stronger and stronger, and they become like bigger bubbles that are now more powerful and can lift heavier fluids to surface, and they increase my production. So in continuous gas, I'm using the maximum, okay, capabilities of the gas I'm injecting by reduction of the hydrostatic fluid level, expansion of the injection gas because the gas will expand, and the displacement effect because typically the big gas bubbles will be able to lift the hydrocarbons and push it with it all the way up north. And I'm using the floating effect where the gas will float, move up, and it will take the fluid all the way up. In the case of intermittent gas, I'm not using all three methods. I am only using the method of displacement. Okay. And typically, intermittent gas will be used on low reservoir pressures, pressures that are relatively low, and production rates that are typically low as well. And in this method, because I'm only using the displacement, okay, I will be initiating large bubbles of gas. And this large bubbles of gas is what will enable me. These large bubbles of gas is what will enable me to lift entire fluid columns all the way up. And it is frequency and time related, and it is producing with a cyclic nature. And this production of cyclic nature makes intermittent gas lifting not really a favorite thing. Okay? And we will go in the next couple of slides in detail to know what is the reason, okay, intermittent gas is actually not used a lot. So let's compare both, okay? Continuous gas lift and intermittent gas lift. In continuous gas lift, okay, it has high efficiency as compared to the intermittent gas. It is less expensive, even though you're pumping continuously, it is actually less expensive. And you actually end up spending less gas, okay? Because you're pumping less gas, but at continuous flow rates and low flow rates. And this is what makes it most widely used worldwide. In intermittent gas, it's actually less efficient. And you end up spending and using more gas, okay? Because you have to be pumping big volumes of gas at high rates in order to initiate big gas bubbles from the start to be able to lift the fluid part or fluid sector. The second thing, it's cyclic, okay? Now, in the next couple of slides, we will go into how continuous gas lift is applied and how intermittent gas lift is applied. So we will start now with continuous gas lift application. And we will start with a case of a well. And typically the well will have liquid both inside the annulus and inside the tubing as well. And we will start now with step one by pressuring up or injecting gas in the annulus. And once we start injecting, we will now start the displacement process, and the fluid is now being pushed in from the annulus into the tubing, and it will also start to initiate a delta P, a differential pressure, because as the fluid level moves down and the annulus will have gas while you still have liquid inside the tubing, you will now initiate a delta P, and this delta P will initiate the first gas lift valve to open. And we'll take it step by step. As we open, we're injecting more gas, and then the fluid level will move a little bit down and down. And then when this moves down, it will initiate this valve now to start circulating, and the gas will now start entering through this valve and lighten the hydrostatic fluid column above the depth of this valve. And then we keep on injecting gas again up until a point where the gas will reach the second gas lift mandrel. And when that happens, obviously within this process, we are reducing the hydrostatic level line and the hydrostatic pressures across. And I will reach a point where the gas will now start to come in and lighten the fluid column starting from this depth, the depth of the second valve. And once I have done that, the first valve will now close because the first valve no longer has any delta P across it, because it will have gas in the annulus, and inside it, it has a lightened fluid column because there's already gas and it has previously lightened the fluid column up to that depth, then I will start dealing with the gas being injected in the second valve. And then I will keep on injecting gas again into the annulus up until the lowermost valve will open. And when the lowermost valve will open, it will now start reducing the hydrostatic head all the way throughout the tubing. And I will now have reached my optimum point where this valve, the first valve has already closed, the second valve has already closed, and the bottommost valve will stay open, and it can stay open for a very long time because this is now the name of the game. It will keep on injecting gas, and this is now the gas entry point into the tubing. And within this process, I have now reached this magic line, and this magic line is much, much better than the previous line where the line was not even reaching up to the wellhead depth or the reservoir pressure or the wellhead pressure. So how about an intermittent gas? We finished the continuous, and now what's the case of intermittent gas? Why is it that nobody really likes it, and why is it expensive, and why is it not used much? So in intermittent gas, you will have this intermittent gas lift systems. You will have the same system, okay? Now note that the valves are initially closed here. You will inject gas here, and you will have a small orifice valve at the bottom. And once you start injecting gas all the way and this orifice valve opens, okay, you will now initiate a liquid or fluid column to start coming in. And this liquid or fluid column that has come in will start to make its way to the top or to the surface. And you keep on injecting, and the orifice valve will now close, and the gaslet valve will open, and you have now shifting the oil bubble or the oil column a little bit more north and a little bit more north. And in this process, you have already spent quite a lot of gas because it's just based on the displacement process. You're not using the advantage of expansion. You're not using the advantage of the actual concept of gas lifting. Okay, you are spending quite a lot of gas to shift this bubble all the way to surface up until it reaches the separator. So that's this part of the difference between the intermittent and the continuous gas lift systems. Now let's start talking about the applications. Okay. Now this is an introductory webinar, so it's basically introduction, but I'll try to go through as much as I can. So the main application for gas lift is basically you need to know the valve depth calculation, and we will summarize it here in 3 steps. We go over them one by one, step by step, easy, and slow. First of all, you need to know how to calculate the depth of the point of gas injection. And to do that, you have to know the injection gas pressure, which will always be given and is provided because this is gas coming from the station, and the expected production, which you can previously have been doing the IPR exercise, and you know your expected production, what's your aim of production, and we will go through a small example of how to calculate the point of gas injection. Once you know the point of gas injection of the first valve, then you can calculate the depth of the remaining valve, a concept of applying the delta P's all the way up. And you should also be able to know how to calculate the setting pressure of the valves. Okay, so let's go over them one by one easy. To calculate the depth of the point of intersection, this is the case as is before gas injection. And before gas injection, you will have a static gradient, and this is the static fluid level, which in all my previous slides, I'm saying that the well is weak. It cannot deliver to the surface. It cannot deliver. The well can only be holding a static fluid level below the surface and below the wellhead. And you will have your injection gas gradient, which is, let's say that this is similar to the gas you are injecting inside the annulus. And these two will intersect at a point, but still my problem is with this static gradient because this static gradient is not reaching to surface. And let's take it now step by step and see what we do. So the first thing, I will come to this static gradient line and I will apply a drawdown of 400, let's say for an example, 400 barrels per day, and I can calculate the 400 barrels per day actually matches how much delta P on the axis of the pressure. And once I draw this delta P, which is corresponding to 400 barrels per day, then the next thing I'm going to draw a parallel line to the static gradient line. Okay. And after I have done that, I will then go and draw the gradient line of that's corresponding to 400 barrels per day, and I can obtain this line or this curve from the Dilbert plot, for example. And once I draw this 400 barrels per day line and this 400 per day barrel drawdown line parallel to the static, I will have a point of intersection, and we will keep this for now. And then the next step, I can repeat this step again, and I will draw a drawdown. I will calculate this distance, which is matching a delta P here. And this delta P will be corresponding to a 600 barrel per day drawdown. And then once I have that, I will draw a line parallel to the static gradient. And once I have that, then I will go again to the Dilbert plot, for example, and bring my 600 barrel per day line. And here I will have another point of injection. Now, these 2 points of injection are now actually starting to formulate what my gas lift performance will be. And this will take care of the calculation of the points of gas, because now I have 2 gas injection points. And the next thing, I can bring all my points, which I have together, and then I will join them. And when I join them, I will obtain a line, which is my dream line, the line I've been working to draw all the time. And this line will represent a line which will represent flow to the wellhead with positive pressure. Okay? Very good. And from there on, I can be calculating the depth of the remaining valves using the same method. Okay? Of all the valves that I will need. Okay. And then the setting pressure of the valve is very simple. From the same plot which you see here, I will basically take a line up from here and take a line which is the intersection with my actual gradient line of my gas, and this delta P will represent my opening pressure of my second valve. And if I want from a third valve, I will come to this point here and calculate the delta P from here. Okay. All right, so let's go a little bit more in depth with other gas lift applications. And the main problems with gas lift applications is scale accumulation. And scale is very prone to accumulate. It really likes the pockets, it really likes the mandrels, it really likes the springs inside the valves, and scale will accumulate. It will cause a lot of problems. Obviously, high grades, and then both of these will affect the valves. A lot of them will be stuck open or stuck closed. But it's still not a worry, even though they are prone to problems, it's still not a worry. Still, a lot of operators like them, a lot of producing companies like them because they're very cheap to change. It's all, you can use stickline, and stickline is a relatively cheap application, and stickline operators can really change gas lift valves. You can change all the gas lift valves within less than 2 or 3 hours if everything is smooth. And then there's the monitoring techniques. So in the olden days, okay, because gas lift, as I mentioned before, is a very old technique. It used to be the Martin-Decker chart, which is still okay. Some people still use it. Okay, gas lift application as a whole is very popular in countries such as Algeria, Egypt, India, okay, where you have big fields with low reservoir pressure. But a new technique has come up recently, which is real-time temperature surveys. And this is causing a revolution in gas lift monitoring because It's much easier than the previous method. It's really unique and very easy. You just run into the well completion with the real-time temperature survey. It's basically a fiber optic line, and it will sense temperature, and it will give you a temperature survey. And I will show you now how you can use these temperature surveys to troubleshoot your gas system. And obviously, the most recent introduction to GasLift is basically software designs, and almost all production softwares now that are available at commercial level do have options where you can design the total GasLift systems in terms of depth, in terms of delta P's across the valve. So let's take a look at this example or this application. And in this example, you have a well with, let's say, 3 valves, and this will be the typical, okay, temperature survey. And this temperature survey at the beginning, before I start, it's okay. All right. And then we start the gas injection, and then the bubbles, I start to inject gas in the annulus, and the valve opens and the bubbles start coming in, so the hydrostatic pressure starts to reduce. And with hydrostatic pressure reducing, it will be sensed in the temperature as well. So if I run my line, my survey line to the well depth, I will note a kink here in the curve of the temperature, and this is a good signal because that means that this valve has opened and the other valves are not open yet, which is okay because I'm still in the starting process. And then as I start injecting the gas more into the annulus, my second valve will start to open, my first valve will stop, which is okay. And I will note a bigger kink here because this valve has more gas flowing through it. That's good. I will note a smaller kink here because this valve is almost in the closing stage. And if you look here across this valve here, you will note that there's no kink. That means that this valve is closed and this valve should be closed and things are okay so far. Okay, and then at the very end, okay, my bottommost valve, my injection valve, okay, will be open, it will stay open, and my top valves are closed, so I'm okay. And as you look at this, the temperature survey, which is in green here, I have a very big kink in the temperature, a very big change in temperature, and almost no kinks here, so that means that my system is working well and I'm okay. So how about if the case of things are not okay? All right. If we take a look at this example, okay, here this valve is working and I can sense a big kink here across the valve, which is okay. It's a good sign. And then I have a kink here and another kink here, okay, in the temperature survey. And this is not good because this means that I have these 2 valves leaking. These valves should be closed when this valve is operating, and then this is where I have already troubleshooted the system. I know that these 2 valves are leaking, and you can ask Slickline to come and change these valves with better valves. Okay. All right. Now, there's also another way to do gas lift. I mean, we said about the previous system where you can have multiple gas lift valves in the completion. Well, there's another method, a much easier, simpler method, which is used very well in countries such as Algeria and in India as well. And basically, their sorts of reservoirs are different, and they apply gas lift without using gas lift completions. They use the same completion without gas lift manuals. They just run something in called the velocity string, and the velocity string is basically a piece of tubing. They run it in, and at a certain depth, they start injecting gas, and this is enough to apply the delta P, which is required to lift and reduce the hydrostatic head, and the reservoir pressures there are marginal, so they're not strong and they're not weak. But that's it, the concept is there, and it's working, and it's working very well. And I know a lot of fields in Algeria that are using this concept of velocity string. Basically, they run a velocity string in, they pump the gas into it, and in some cases, if they have scale accumulation in the completion, they can pump fresh water and dissolve the salt as well. And it's another way, or it is a known concept of applying a simple gas lift, okay, without the use of gas lift handles or gas lift valves. And typically, if you run a temperature survey here, you would just have the kink at the point of gas injection. Okay, so that's it for today. I hope it was short and sweet, summarized. I hope that you have learned something from me and that it was enjoyable. And I wish you all the best of luck in your internships, in your future careers. And I pass the floor now to Mohammed and to any of you if you have any questions.
Thank you so much, Dr. Ahmed. We all would like to thank you for the amazing webinar you presented today. We have received many questions, but I have collected the most important ones or most common ones. So the first question is, what are the consequences if the inflow and outflow curve does not intersect each other?
Okay, so if my inflow and my outflow curves do not intersect, then I need to start analyzing the problem, okay, in two ways, okay? Either I will decide to change, let me try to take you to the slide that this represents this. And I think uh, this one might be best. Okay, so if my outflow and my inflow do not intersect, that means that I have a problem in delta P. And one of them needs to move. Okay, they have to meet because if they don't meet, we don't have a solution point. One of them has to sacrifice and move, take a step towards the other. All right. So either I will decide to move. Let me see if I can get a pointer here. Okay. So either I will decide to move my my inflow curve to intersect my outflow. So I have to shift the inflow curve up. And the inflow curve, as I mentioned before, is related to reservoir pressure. And meaning that you're going to deal with reservoir pressure, you're going to be dealing with big money, okay? Because you will either have to be doing gas injection or water injection, and it's a big investment. It might be worth it, go ahead, okay? But moving the inflow up to intersect with your outflow, it's a big investment. All right. Sometimes it's done, and it is done in big fields in Saudi Arabia, Gafar Field, uh, even in Algeria. Okay. The movement of the inflow curve is an option. The reservoir producing potential does justify the investment, and yes, a lot of operators and oil companies will put the investment to move the inflow to intersect outflow. Now, if you are in marginal fields that are economically not, you cannot really justify the big investment of shifting the inflow curve by applying water injection or gas injection, then your next option would be to try to move the outflow curve to move and intersect your inflow. And this will typically be taking you into cheaper options, okay? Because these cheaper options will typically be reperforation, acidizing, or fracturing. And these are things that will move your inflow a little bit, not much, okay, but they will intersect your outflow. And obviously, the methods that you can be doing to shift your outflow to intersect your inflow are, it's much cheaper than the previous methods. I mean, you can either be changing tubing sizes, reducing tubing friction, or artificial lift methods, and typically they fall within the economic acceptance of marginal fees. Okay, does that answer the
Thank,
question?
thank you so much for the answer. And I have received another question that someone is asking how much time interval, minutes, hours, between the opening of one valve and the next valve is needed.
Okay, so first of all, you need to know if you're doing continuous gas lift or you're doing intermittent gas lift. And there are actually methods that can be done to calculate the time because typically intermittent is cyclic and it is time related, right? But if we take the most common method, let's say the continuous gas lift system, the time between one valve to open and the second valve to open is time related, but the ball is in your hand because you are the one in control of the gas being injected, the rate and the pressure of the gas being injected. And what will dictate that more is because depending on the rate you are injecting your gas and the pressure you are injecting your gas, it will automatically dictate the rate at which you are reducing the hydrostatic pressure inside the tubing. And it is this delta P, okay, that will be time related. If you're injecting high rate at a high pressure, then obviously you will be moving the reduction in hydrostatic head at a much quicker rate than if you are pumping your injection gas at a lower rate and a lower pressure.
Thank you so much. The last question. Someone is asking, is that possible to use more than 3 valves in gas lift method? And where is the location of the gas lift valves between tubing joints or in the surface of tubing?
Okay, so for the first part of this question, yes, in my examples, I just stayed with 3 valves just to use simplified example for the purpose of this introductory webinar of gas lift. But obviously, in real life, you can have 5, you can have 7, and you can go definitely more than 3. Okay, it is actually related to the depth of the well. Obviously, you know the depth of your well, you will draw your curves as I did in my previous example. And from there on, this is what will dictate the total number of valves you need. So that's for the first part of the question. Now, for the second part of the question, where are these gas lift valves located? So typically these valves are seated inside a housing, which is called a gas lift mandrel. And within this gas lift mandrel, the valve goes in and sits, all right? And this mandrel is installed, okay? Let me see if I have a picture of one of them. Okay, yeah, maybe this one. Okay, and okay, yes, we can take this as an example. Do you see this slide? Or better even this slide. This would be the picture of the valve, and the valve will actually be seated fully inside what's called a gas lift mandrel. Okay, so you see the slide. And the mandrel will be installed in between 2 sets of tubings. So while you're running the completion, you will have one full tubing, and then you will put a gas lift mandrel and another one on top of it. So in between, okay, 2 joints of tubing. Okay.
Thank you so much, Dr. Ahmed. We really appreciate your presentation and we enjoyed it. Thank you so much for the presentation. And thank you so much, guys, for watching. And we hope to see you tomorrow in the other webinars. Thank you so much, Dr. Ahmed.
Okay, thank you, Muhammad, for being the moderator and moderating it very efficiently. Dr. Al-Garhi, thanks as well. And I hope everyone had learned something from me, and it was short, sweet, and enjoyable. And all the best of luck in your studies and your future careers as well.